before we go on, let's talk about Gauss again for a minute. So I would have thought if I watched the video, there's these videos called 1 blue, 3 brown something. I don't know if you've seen them. They're wonderful. And I thought there's no way they're going to teach me something about the square root of -1. But they had a video that was really quite great. It gave a different definition. Just said I is the vector coming up. And then it proved that multiplying is rotating. So if you rotate twice, then I times I is -1. That's cool. Anyway, here's I. And here's a complex number. And you multiply it out like that. And so our problem here is we have 4 real numbers, and we want to calculate these 2 real numbers. But multiplying cost us $1, and adding cost us a penny, right? So so what's our time? Well, the obvious algorithm is 4 multiplications and a bunch of additions, and we're good, right? But can we do it cheaper? And in this algorithm, we'll multiply those, we'll subtract those, so we have our first number. And then we're going to do this weird thing where we add them and multiply, and that gives us just a number, right? But if we think about it algebraically, it has these 4 components. And note that we know AC, so we can subtract it off. We know BD, so we can subtract it off. And that gives us this, which is our other number. Right? Everybody buy that? And so then that's just subtracting it off. And we did it with 3 multiplications. Right? Everybody good? All right, so the question we could ask is, well, that saved us about 1/4 of the work. And however, we only care about big O notation. So the question is, does this matter? All right? Let's go on to a different topic, which is he's a great mathematician and songwriter. He sings about math. Anyway, that first one I had to fix. But anyway, they add, right? You know how to add. And you can add in linear time, right? So then we can ask, can you add faster, right? Can you add in square root of n time, right? So one way I've talked about running time is the relationship between the algorithm that just looks at the input and the algorithm that solves the problem, right? So just the look at the algorithm takes order n time, right? So the question is, can you multiply without looking at the entire input? No, right? You can't. You got to look at all the bits of the input to know, right? So that's what we're saying here. No, just to read the input takes linear time. So we can add in linear time. We're not going to do any better than that, right? Remember we did the matrix and the matrix searching one, and it ran in square root of n time because it didn't look at the entire input. All right, so that's great. We got addition down. Multiplying seems to take in squared time, right? So multiplying is harder than addition. Is it? Well, certainly quadratic is worse than linear, but we haven't proved that you can't multiply faster, right? Maybe you can multiply faster. In fact, you can. We're going to come up with an algorithm here that's kind of hacky. Some Russian dude did it, and it's. But then you can do even faster methods. You can do it in n log n time using fast Fourier transforms. All right. So now we're going to do that slightly faster method, and then I'll wave my hands around as saying, kind of, if you extend that, you can get down to sort of argue that n log n is possible. But really you do the fast Fourier transforms, which views the number as a polynomial and then views the polynomial as a sum of sine waves, and then somehow magic happens. All right? We're not going to cover that one, but I have slides on it if you want them. All right, so this is a review I'm pretty sure we did already, so we're not going to spend too much time on it. It's just showing that the kindergarten algorithm takes exponential time. Remember that? So we did all of this already in exponential time. We did all this. All right, so here it's just saying, right, the kindergarten algorithm's exponential, the n-squared algorithm, the high school algorithm, and we're going to try to get a little closer to linear, right? And like fast Fourier transforms is n log n, and it's just a hair slower than linear. All right, so we're going to do recursion, as you've seen already. All right, so now the input x, we can view it in two different ways. And we're going to want to be switching back and forth. And what's the, we want to think of it, one way to think about it is an integer, right? But in reality, the integer is so big that you can't, we're only going to do this algorithm when the input is bigger than fits in the computer, right? So how is it stored? It's stored as a sequence of digits, right? So really the input is a string of characters, but 4 characters in this case. But, you know, our way of, we're thinking about it as an integer, right? All right, so now we have to have a recursive program is going to give each friend a smaller instance. And remember I said if the input's a value, you never want to subtract 1, right? But you want to divide the value by 2, right? But here we're going to do something even more extreme. Instead, we're looking at the digits. Now, digits, it's okay to subtract off 1 digit. But we're going to be even more big. We're going to divide the number of inputs, the number of digits in half, right? So here, we're going to take A and B to be the first half and the second half. So we can view these as two different ways. They can be strings of characters, right? This is the first half of the characters of X, and this is the second half of the characters of X, right? But we can also think about them as values, right? And then you need to know the relationship between the A's and the X, right? So here, if you take the 21 and you want to shift it in over 2 places, right? Because here n is 4, so we want to shift it in over 2 places. So you multiply it by 10 to the n over 2, right? And then you add on this, right? Everybody buy that? And all right, so in fact, the value from x to a is more like a square root, but that doesn't matter. All right? Everybody good with that? This is showing it again. Oh. And we do the same with y. All right, those are our numbers, and our goal is to multiply them. And so let's multiply them algebraically so that we can prove things. We multiply them, and we get these various parts. So, I don't know, when I was doing this talk yesterday, it was hard for me to come up and explain that this example really helps. But the point is, right, that you take the 3 times the 2, and you get 6, and you don't shift it. And at some point, you have to do 3 times 1, which is 3. And I'm not, oh, here's the 3, and you're shifting it once, right? And the 2 times 2 is 4, which is shifted once. And the 1 times 2 is 2, which you shift twice. Right? Does that make sense? So actually, that I was able to understand it that time. I didn't do as well yesterday. So everybody see that? And so here's our equation, right? And again, it's taking this times this without shifting it, and this times this and shifting it by n over 2, and this times this and shifting it by n over 2 twice. Right? Everybody? So anyway, that's our equation. And, oh, and here's our code. All right, so what's our code? Now, what do we mean by absolute value signs? You have to sort of figure out what it means, right? So if it was a negative number, maybe it makes it positive, right? But often we use it to be size of. Now, what's the size of x? Well, the size of x could be the value of x. But here I'm talking about the size of x being the number of digits, right? So here I'm just trying to spit it into small code which says if x is 1 digit and y is 1 digit, then just table lookup, know how to multiply them, right? Otherwise, you take your x and you break it into a and b, and you take your y and you break it into c and d, and then we do what we did there. We have a friend here, a friend here, a friend here, a friend here. We have 4 friends. Those we add and shift. These we shift. That we don't shift. We add it all together. Everybody get the algorithm?